Welcome back to Data Deep Dive, where we explore the latest and greatest in the world of data science. Today, we're diving into the fascinating realm of time series forecasting, and I'm joined by two incredible guests. Oscar, one of the lead researchers behind the groundbreaking paper NeuralProphet, Explainable Forecasting at Scale, and Catherine, a seasoned data analyst who's seen the power and challenges of time series forecasting firsthand.
Thanks for having me, Amelia. It's great to be here.
It's a pleasure to be here, Amelia. Time series forecasting is a critical area, and I'm always excited to learn about new advancements. Absolutely, Catherine. And that's precisely why we're so excited to have Oscar with us today. Time series data is everywhere, from predicting energy demand to understanding customer behavior. And having accurate and reliable forecasting models is absolutely essential for businesses and organizations. You're right, Amelia. Traditional forecasting methods have their limitations. They often struggle with complex, nonlinear patterns in the data, and they can be difficult to scale to handle the massive data sets we see in today's world. We need forecasting models that are not only accurate, but also explainable and adaptable, which is where this new research comes in. That's exactly it, Catherine. Oscar, let's dive into the paper. Can you tell us about NeuralProphet and its key contribution? It's described as a successor to Facebook Prophet, so what makes it different?
Of course, Amelia. NeuralProphet is built upon the foundation laid by Facebook Prophet, which was a major step forward in making forecasting accessible and interpretable. But NeuralProphet goes further by incorporating the power of deep learning. It's a hybrid framework that combines the strengths of traditional time series models with the flexibility of neural networks.
That's intriguing. Can you elaborate on the modular design of NeuralProphet? How does it break down the forecasting process?
Think of NeuralProphet as a Lego set for time series forecasting. It's composed of different modules, each contributing to the final prediction. We have modules for modeling the trend, seasonality, events, future regressors, and even the autoregression and lagged regressors that Catherine mentioned earlier. Each module can be individually configured and combined to build the most suitable model for your specific forecasting task.
That sounds very flexible. Let's talk about these modules in detail. Starting with the trend, how does NeuralProphet model it?
The trend module captures the overall long-term direction of the time series. We use a piecewise linear approach, which means that the trend can change direction at specific points in time called change points. This allows us to model nonlinear trends that traditional methods might struggle with.
So, it's like fitting multiple linear lines together to capture the trend's fluctuations.
Exactly. And the beauty of this approach is that it's very interpretable. You can see where the trend shifts and understand how the growth rate changes over time.
Interesting. And how about seasonality? How does NeuralProphet account for cyclical patterns?
We use Fourier terms to model seasonality. It's like decomposing the cyclical pattern into different frequencies, allowing us to capture both regular seasonalities like daily, weekly, and yearly cycles, as well as more complex, non-integer periodicities.
That's a bit technical. Could you give an example of a non-integer periodicity?
Sure, imagine you're analyzing data with daily frequency, but you want to model the yearly seasonality. Since a year isn't exactly 365 days, it's considered a non-integer periodicity. Fourier terms allow us to handle these cases smoothly.
That makes sense. And what about events? How do you account for sporadic occurrences that might influence the time series?
The event module handles these one-off events. We represent them as binary variables. Either the event happens or it doesn't. This allows us to model the impact of holidays, promotions, or any other unique events that might affect the time series.
So, if we're looking at retail sales data, the event module could capture the impact of Black Friday or a major holiday sale.
Exactly. And we can even model the impact of the event for a specified window around the event itself. For example, we could account for the impact of a holiday sale, not just on the day of the sale, but also in the days leading up to it.
That's a very practical application. And what about future regressors? How do those fit into the picture?
Future regressors are external variables that we know the future values of. For example, if we're forecasting energy demand, we might know the future weather forecast. The future regressor module allows us to incorporate this external information into our predictions.
I see. So it's about incorporating additional data points that could potentially influence the target variable. Very useful for capturing dependencies. Exactly. Now, let's delve into the more advanced modules. Catherine, you mentioned autoregression and lagged regressors earlier. Can you elaborate on why these are important for time series forecasting? Absolutely. Autoregression is all about capturing the inherent dependencies within the time series itself. In essence, it's about regressing the future value of the series on its past values. For example, if we're looking at stock prices, the autoregression module might capture the tendency for a stock to continue trending in the same direction for a certain period of time. So it's like looking for patterns in the past behavior of the time series to predict its future behavior. Exactly. And lagged regressors are similar, but deal with external variables. Instead of looking at the past values of the target series, we look at the past values of other observed variables, or covariates. For example, if we're forecasting energy demand, a lagged regressor might capture the impact of past temperature fluctuations on the current energy demand. I get it. It's about taking into account the impact of related variables on the target variable. So for sales forecasting, we could use lagged regressors to incorporate past marketing campaign data, for instance.
Absolutely. And the beauty of NeuralProphet is that it can model these relationships using either linear or nonlinear models depending on the complexity of the data.
That's amazing. So we've explored the modular design of NeuralProphet. Let's talk about how the model is trained and how it handles data. Oscar, can you explain the pre-processing steps involved?
Sure, Amelia. Before training, we need to address any missing data and normalize the data for optimal training. For missing data, we use a combination of linear interpolation and rolling averages. This helps to minimize data loss while preserving the overall pattern of the time series. And for normalization, we offer several options like min-max scaling, standardization, and a soft scaling method that emphasizes the tails of the distribution. These normalization techniques help to prevent issues with numerical instability during training.
And how about the training process? What makes NeuralProphet's approach different from traditional time series models?
Traditional models often rely on gradient-based optimization methods like LBFGS. NeuralProphet, on the other hand, takes advantage of the power of deep learning and uses mini-batch stochastic gradient descent, SGD, for training. This approach is well suited for large data sets and allows us to incorporate more complex model components, like the neural network modules for autoregression and lagged regressors.
That makes sense. And what about the loss function? How does NeuralProphet evaluate the model's performance during training?
By default, we use the Huber loss function, which is a robust alternative to mean squared error. It's less sensitive to outliers, which can help prevent the training process from being derailed by noisy or extreme data points. We also provide options for using other loss functions like mean absolute error or custom functions, depending on the specific forecasting task.
And what about regularization? How do you prevent overfitting?
We use a scaled and shifted log transform of the absolute weight values for regularization. This helps to encourage sparsity in the model's weights, which means that less important features are assigned weights closer to zero. This helps to reduce overfitting and improve the model's generalization ability.
So it's like pruning the model's connections to focus on the most relevant features.
Exactly. And we also use a one-cycle policy for the training schedule. This involves gradually increasing the learning rate during the early stages of training and then annealing it down towards the end. This approach has been shown to significantly speed up training and improve the model's performance.
This is all fascinating. Oscar, let's shift gears and discuss the results. What did you find in your experiments?
We conducted two sets of experiments, one using synthetic data to assess the accuracy of the decomposed forecast components, and another using real-world data sets to evaluate the overall forecasting performance. In the synthetic data experiments, we found that NeuralProphet consistently performed as well as or better than Prophet, especially when modeling autoregression and lagged regressors.
So, NeuralProphet is particularly good at capturing those dependencies within the time series?
Yes, that's right. And in our real-world benchmark, we saw that NeuralProphet, especially when using autoregression, significantly outperformed Prophet across a wide range of datasets and forecasting horizons. We also found that the model's performance was not overly sensitive to the specific number of lags or the configuration of the neural network modules.
That's very encouraging. Catherine, from your experience, how would you say these results might impact forecasting in real world applications? I think NeuralProphet has the potential to be a game changer. The fact that it's so explainable and scalable is crucial for businesses. Imagine a scenario where you're forecasting energy demand. With NeuralProphet, you can not only get an accurate forecast, but you can also understand how different factors, like temperature, weather patterns, and past demand, are contributing to the forecast. This kind of insight is invaluable for decision making. And it's not just about energy. NeuralProphet could be used in a wide range of industries, from retail and finance to healthcare and transportation. It's a versatile tool that can handle a variety of forecasting tasks. And the fact that it can be easily extended and adapted to new research is another significant advantage. That's an excellent point. Oscar, are there any limitations to NeuralProphet that you'd like to acknowledge?
Of course, NeuralProphet is still under development and we're continuously working to improve it. For example, currently it focuses on univariate time series. Extending it to handle multivariate time series is a priority for future research. We also rely on heuristic parameter selection. Developing more sophisticated hyperparameter tuning techniques is another area where we're exploring improvements. And while NeuralProphet is scalable, it can require more computational resources than traditional methods, especially during training. We're working on addressing this through efficient implementations and potentially exploring the use of GPUs for training.
Those are valid points. Catherine, what are your thoughts on these limitations and their potential impact on the adoption of NeuralProphet? While the limitations are worth noting, I believe the benefits of NeuralProphet outweigh them. The need for explainable and scalable forecasting models is growing, and this paper is a significant step in that direction. I'm optimistic that as the research continues, NeuralProphet will become even more robust and versatile, making it a powerful tool for forecasting in a wide range of settings. That's a great perspective, Catherine. Oscar, to wrap things up, could you offer a final reflection on the significance of NeuralProphet and its impact on the field of time series forecasting?
NeuralProphet represents a significant advancement in making forecasting more accessible and reliable. It builds on the foundation of Facebook Prophet by incorporating the power of deep learning, making it more adaptable and capable of handling complex data patterns. I believe it has the potential to democratize forecasting and drive further innovation in the field, making it possible for a wider range of users to benefit from advanced forecasting techniques.
That's a powerful statement. I'm sure our listeners are eager to explore this research further. Thank you both, Oscar and Catherine, for such a comprehensive and insightful discussion. This has been a fascinating dive into the world of time series forecasting, and we're excited to see how NeuralProphet continues to evolve in the future. Stay tuned for more exciting discussions on Data Deep Dive.